Hello everyone and welcome to this online lecture for CE 105. So today what we are going to talk about the stiffness of glasses. So what controls the elasticity of glasses? So the stiffness of glasses is important. So the stiffness tells you about if you apply a given pressure or a given stress on glasses, how much will they deform? And here we are talking about reversible deformation. So you apply a stress, the glass will deform. When you remove the stress, the glass comes back to its original shape. So what we'd like to understand is those kind of elastic deformation, those kind of reversible deformation, how can we quantify them? And the extent of deformation that you get for a given stress, how is this controlled by the structure and composition of glasses? And at the end, what we'd like to understand is what is the atomistic origin of this? How can we understand the origin of the stiffness of glasses based on the energy applied by the atoms on each other? So let's start by a few reminders about elasticity and stiffness. So the first thing that we would like to see is what are the quantity, the metrics that can characterize the stiffness of a given glass. So we'll talk about the bulk modulus, Young modulus, Shear modulus, Poissons ratio, etc. And how in practice do you measure the stiffness of a glass? So as a reminder here, we are talking about reversible deformation. You apply a stress, the material deforms because of the stress, and then you remove the stress, the material will recover its initial shape. Okay, so this is a reversible deformation. Material can also deform in an irreversible way, but this is not controlled by the elasticity. This is controlled by the hardness of the glass. So here, what we want to understand is what is the extent of elastic reversible deformation once you apply a stress on a given glass. And the first thing that can be measured is the Young's modulus. So the Young's modulus is the quantity that characterizes the resistance of a glass or of a given material to uniaxial deformation. What does it mean is that you take a given material like this cylinder here, you apply a stress that is on the longitudinal axis. So you apply a stress like this that can be a tensile stress or a compressive stress along the longitudinal axis of the material. So this would be the longitudinal axis. So you apply a normal stress, a stress that is normal, that is perpendicular to the surface over which it is applied. When you apply a longitudinal stress like this, it will tend to elongate the material if it is under tension. It will tend to compress the material if you put it under compression. Okay, so in this case, the material will change its length. Okay, and the extent over which the length is changing depends on the stress and depends on the Young's modulus. So in that case, if you apply, for example, a tensile stress, so you apply a force like this that tends to elongate the system, then you get an elongation delta L. And if L was the initial length of the material, then you can define the longitudinal strain or the normal strain, which is epsilon, and it's defined as the elongation divided by the initial length. Okay, so this by convention, a positive strain, positive normal strains means tension, which means that you will have an elongation. A negative strains means compression, means that you will have a shrinkage of the material. The dimension of the material will decrease. So which means that in this case, tension, the length is increasing, delta L is positive. In the case of a compression, the length is decreasing, so delta L is negative. Then the question is, how does it relate to the stress? So in this case, we are applying a normal stress. The stress is the force per unit of surface. So the stress is defined by the force divided by the area over which the stress is applied. So in this case, the area is here the cross-section of the cylinder. This is the area over which the force is applied. And now what the Hooke's law tells us is that there is a linear relationship between the normal stress and the normal strain, and that the coefficient of proportionality is the Young's modulus. So what you can write is that the normal stress, as long as you remain in the elastic regime, so in the range of stress for which the stress is proportional to the strain, you can write that the stress is increasing linearly with the strain, and that the proportionality constant is the Young's modulus. In that case, if you plot stress as a function of strain, you have a linear relationship where the slope is the Young's modulus. And this is going to be valid for the range wherein the glass is elastic. Of course, if you increase the stress or the strain so much, and then at some point you will have a yield point or even fracture, but for the range which is the elastic range where the stress is proportional to the strain, then the Hooke's law is valid, and in that case the relationship between stress and strain is a linear relationship, with the proportionality constant being the Young's modulus. So the Young's modulus tells you for a given strain or a given stress, for example, if you take a given stress, what is going to be the corresponding deformation epsilon. So the higher the Young's modulus, if you have a higher modulus, then you have a higher slope here, which means that for a given stress, you will get a lower deformation, or you will need a higher stress to reach a given deformation. So typically, the higher the Young's modulus of a material, the lower will be the amount of deformation that this material will show for a given stress. The second stiffness parameter that is very useful is the Poissons ratio. So again, Poissons ratio can be calculated when you have a material that is subjected to a uniaxial tension or compression. So again, in this case, you take a given material, you apply a tensile force, a longitudinal tensile force in this case. Then in that case, two things will occur. Okay, so here the dash lines is the initial extent of the material. The first thing that is going to happen, as we just saw, you will first have an elongation. So you will have an increase of the longitudinal length of the material. So this is what we saw with the Young's modulus. If you get a normal stress, if you have a normal stress sigma, then you will get a normal strain epsilon, so you will have an elongation of the material. So this is controlled by the Young's modulus. But the other thing that will happen is that the material will shrink laterally, which means that in this case, if this is the initial width of the material, d, this width will decrease. This is because the material wants to keep its volume constant. So if it is elongated on the longitudinal direction, then it will want to shrink laterally to try to keep its volume constant. So in that case, you have two kinds of strain. You have the longitudinal strain. The longitudinal strain is defined as the relative elongation, so the change of length delta L divided by the initial length L of the material. And you have the lateral strain. The lateral strain is the change of the lateral dimension divided by the initial lateral dimension. Okay, so this is what happens on the longitudinal direction, and this is what happens on the lateral dimension. So there is a relationship between those two deformations. If you apply a tensile stress, usually the material will elongate on the longitudinal direction, but it will shrink on the lateral direction, which means that if you apply a tension, it means that the longitudinal strain will be positive. Why? Because the longitudinal elongation is positive, delta L is positive. On the other hand, if you're applying a compression, so if you're trying to compress the material longitudinally, then the longitudinal deformation will be negative. Why? Because in this case, delta L will be negative. The longitudinal length is decreasing. And the strain of the longitudinal, on the longitudinal direction, so the longitudinal strain, always have a sign that is opposite to the lateral strain. So for example, again, if you apply a tension, the material will elongate longitudinally, so delta L will be positive, but in that case, the material will shrink laterally, which means that delta D will be negative, D is decreasing, and in that case, it means that if delta D is negative, it means that the lateral strain will be negative. If you apply a compression, then in that case, the longitudinal strain is negative because the material is becoming smaller on the longitudinal direction. In that case, it means that delta D will be positive. The material will try to expand laterally to try to keep its volume constant. And in that case, if delta D is positive, it means that the lateral strain will this time be positive. So the longitudinal strain is always opposite sign than the lateral strain. If one material elongates longitudinally, it will shrink laterally. If one material shrink laterally, it will elongate longitudinally. So you have always an opposite sign between the longitudinal and the lateral strain, which means that you can define the Poissons ratio. The Poissons ratio will be the ratio of the lateral strain divided by the longitudinal strain. But since one is always an opposite sign with respect to the other, we add a minus sign so that the ratio will always be positive, so that you have a positive Poissons ratio. Okay, so this is the observation based on that defines the Poissons ratio, which is that when a material elongates longitudinally, it will shrink laterally. That's the first thing. And the second observation is that the lateral strain is proportional to the longitudinal strain, but the proportionality constant is the Poissons ratio, and they have an opposite sign. Okay, so this is based on observation that the lateral strain is proportional to the longitudinal strain. That, based on this information, that you define the Poissons ratio nu, which doesn't have any unit. It's a strain divided by another strain. The next parameter that is useful is the shear modulus. The shear modulus captures the resistance of a given material to shear deformation. So in this case, you are not applying a normal force, a force that is normal to the surface. What you are doing is to apply a shear force. You apply a force that is within the surface, that is tending to shear the material, to change its shape without changing its volume. And in this case, the observation tells you that the shear strain is proportional to the shear stress, just like what you see for the Hooke's law that defines the Young's modulus, but this time this relationship defines the shear modulus. So in that case, first you can define the shear strain tau, which is defined as the force that is applied divided by the area over which the force is applied. So this is the shear stress. And you can define the shear strain. The shear strain is the lateral deformation dx divided by the initial longitudinal length L of the material. So in this case, the shear strain would be dx divided by L, the initial longitudinal length of the material. And same thing, we have the Hooke's law. The Hooke's law principle tells you that the shear stress is proportional to the shear strain, that if you plot the stress as a function of strain, it increases proportionally with respect to the other, as long as you are remaining within the elastic regime. And in that case, the slope is the shear modulus, which gives you an estimation of, for a given shear stress, what will be the corresponding shear deformation. So the higher is the shear modulus, the lower will be the deformation for a fixed shear stress. The last parameter that is useful is the bulk modulus, which characterizes the resistance to a material to change its volume when subjected to a hydrostatic pressure. So in that case, so for the Young's modulus, what matters is when you apply a longitudinal stress, a longitudinal force that tends to either extend or compress the material along its longitudinal axis. In the shear stress, what matters is a force that is applied within the direction of the surface. Here, the bulk modulus characterized when you have a given material and that you apply the same stress in all directions. You apply the same normal stress. So in this case, we are talking of a normal stress, so a stress that is orthogonal to the surface for each direction. In that case, what is going to be the change of volume? Okay, so by convention here, in this case, if the stress is positive, it means that you have a tension. In that case, it means that the volume of the material will increase. If the stress is negative, then it means that you have a compression, and in that case, it means that the volume will decrease. So in that case, what we are doing is that we are going to define the volumetric strain. The volumetric strain is the change of volume divided by the initial volume. So you have your initial volume, and after compression or after tension, the volume is changing. So you have a variation of volume. In that case, if you have a positive normal stress, then the tension, you have a situation where you have a tension, then the volume is increasing. It means that delta V is going to be positive. You have a positive change, a positive variation in the volume. If the stress is negative, then you have a compression. The volume is decreasing. In that case, delta V is going to be positive. If is going to be negative, sorry. If the delta V is positive, then it means that the volumetric strain is positive. And if delta V is negative, then the volumetric strain is also negative. The sign of the strain is defined by the sign of delta V. Then in this case, since the stress is the same in each direction, usually we don't call it stress, we call it pressure. Because in this case, when the stress is the same in every direction, is the kind of situation where first you are in a given atmosphere, just like we are. In this case, the pressure that we are experiencing from the atmosphere is the same in every direction. So same in every direction means that it's isotropic or hydrostatic. Or this is the kind of situation that is experienced when you go underwater. Then the stress that is applied by the water depends on how deep do you go, and in that case the stress will be the same for every direction. It's also an hydrostatic stress. So in this case, when the stress is the same on all the x, y, and z direction, usually we call it pressure. So in that case, a positive stress will also means positive pressure. So in this case, positive stress will mean positive pressure. Negative stress will also means negative pressure. And again, what the Hooke's law tells us is that the volumetric strain is proportional to the pressure that you apply, and that the relationship is that the pressure is proportional to the volumetric strain, and that in this case, the proportionality constant is called the bulk modulus. So just like the Young's modulus, the unit of the bulk modulus will be the unit of the pressure divided by the unit of the strain, but the strain doesn't have any unit. So the bulk modulus will be a force per unit of surface, for example, Pascal, or usually more accurately, gigapascal is the right order of magnitude. So again, in this case, the bulk modulus will be defined as if you plot the volumetric strain and you look at the function of this volumetric strain, you look at the pressure that you are applying. What the Hooke's law tells you is that the strain is proportional to the pressure, or the pressure is proportional to the strain, and that the slope is the bulk modulus. So that for a given pressure, if you have a low bulk modulus, then you will have a large deformation. But if the bulk modulus is higher, it means that if the slope is higher, then for the same pressure, you will get a lower deformation. The volumetric strain will be lower. The good news is that usually glasses are isotropic material. What does it mean? Isotropic means that the properties of glasses do not depend on the direction. So you do not have a direction that is stiffer than another one. For example, if you have wood or if you have reinforced concrete, then you have a direction which is the direction of the fibers that is stiffer than the other direction. In this case, glass, there is no such microstructure, so the properties of the glass, the stiffness, the Young's modulus, do not depend on the direction, so glasses are typically isotropic material. In that case, when you have isotropic materials, then you have some relationship between the different stiffness parameters. You have some relationship between shear modulus, Young's modulus, bulk modulus, Poissons ratio. And for isotropic material, if you know two of those parameters, for example, if you know the shear modulus and the Young's modulus, then you will be able to calculate all the other ones. Okay, so it's enough to know only two stiffness parameters to be able to calculate all the rest. So the relationship in that case is, for example, if you know the Young's modulus and the Poissons ratio, and if you want to calculate the shear modulus, then the shear modulus is given by the ratio of Young's modulus times 2 plus 1 plus the Poissons ratio. So that's the first thing. If what you know is the Young's modulus and the Poissons ratio, then in that case, for example, you can calculate also the bulk modulus. In that case, the bulk modulus is given by the ratio of the Young's modulus divided by 3 times 1 minus 2 times the Poissons ratio. If what you know is, for example, the Young's modulus and the shear modulus, then you can calculate, for example, the Poissons ratio. So Poissons ratio in that case would be given by the ratio of the Young's modulus divided by 2 times the shear modulus minus 1. And last example, if you know the bulk modulus and the shear modulus, then you can calculate the Young's modulus by the following expression, that the Young's modulus is given by 9 times the product of the bulk modulus times the shear modulus divided by 3 times the bulk modulus plus the shear modulus. So you don't have to remember those equations, but the idea is that for isotropic material, it's always enough to know two stiffness parameters to be able to calculate the remaining two parameters. So all you need to know, if you want to predict the stiffness of glasses as a function of their structure, as a function of their composition, it's enough to predict two of them, for example, Young's modulus and bulk modulus, to be able to calculate all of them, to be able to calculate the Poissons ratio, for example. The next question is, how do we measure the stiffness of glasses? And typically one relatively easy way of measuring the stiffness of glasses is to do a three-point bending experiments. How does it work? So you have a piece of glass like this, and you subject it to three-point bending load. So for example, you apply 3 loads like this, so that overall, after deformation, your glass will now be curved because of the three-point load that you have applied. And the idea is that based on the force that you apply, so if you apply a force, the system needs to be at equilibrium, so the vertical force needs to balance each other. You apply a given force, and what you measure is the corresponding deformation, or for example, the corresponding curvature of the glass. And based on the curvature that you measure for a given force, you can back calculate the Young's modulus of the glass. Why? Because if you apply some forces like this, what you effectively are doing is to apply a moment on the glass. So this is something that we discussed in 108. If you have a glass that has a curvature like this, then it means that you are applying a positive moment. In this case, when you have a beam like this, which in this case is just a piece of glass, if it gets a smiley face, then it means that it is a positive moment. On the other hand, if you apply a negative moment, then this corresponds to a sad face that gives you a negative moment. In that case, when you apply a moment to a material, you will tend to curve this material. In that case, if you have a given material, initially it has no load. Okay. After you apply a positive moment, this material will be deformed like this. In that case, the length of the material doesn't change. The length of the material before and after deformation will not change. If you look at the length here of the longitudinal axis, this doesn't change, but the top part of the material has a length that is decreasing, and the bottom part has a length that is increasing. It means that the top part in this case will be under compression, and the bottom part will be under tension. So in the top part, you have a compressive stress, a negative stress. In the bottom part, the stress will be positive. You have a tension stress. And in that case, what we saw in 108 is that the stress that is generated by a given moment m can be calculated as minus m times y, where y is the distance from the middle of the beam, from the neutral axis, divided by I, the moment of inertia of the beam. So if you apply a moment to a given piece of glass, what you will generate is a given stress, a given normal stress within the glass. And then in turn, this normal stress is also equals to the Young's modulus times the strain. So if you are able to measure the deformation of the beam, and if you know what is the moment that you are applying, so if you know the moment, you can calculate what is the stress. So if you know the stress and if you know the deformation, you are able to measure the Young's modulus. In practice, what is done for this is to say that there is a relationship between the moment and the curvature of the deflection of the beam, the curvature of the beam. So, for example, if you try to look at what is the curvature of this thing. So here we can characterize the deflection of the beam by the quantity V, which characterizes the displacement with respect to the horizontal axis of a given point of the beam at a given point x. And then the relationship that we saw in 101 and 108 is that the moment that is applied to the beam is equal to the product of the Young's modulus times the moment of inertia times the second derivative of the deflection with respect to x, where x is the longitudinal axis, which means that this is the curvature of the piece of glass. So if you are able to measure the curvature of the glass for a given moment, and if you know its moment of inertia, then it means that you can calculate, you can back calculate what is the Young's modulus of the glass. So typically this 3-point bending method is what is used to measure the Young's modulus of glasses. Okay, so now we are going to review how the composition and the structure of glasses is affecting their stiffness. So let's start with the example of glasses silica. So in glasses silica, those are the values of the stiffness moduli. So in this case, the Young's modulus is around 70 gigapascal. The shear modulus is around 30 gigapascal. Bulk modulus 37 gigapascal. Poissons ratio around 0.17. Okay, so typically for glasses, for silicate glasses, the Young's modulus will always be between 50 to around 100 gigapascal. Shear modulus between 20 to 40 gigapascal. Bulk modulus between 25 to 50 gigapascal. Okay, so those are typical orders of magnitude. Poissons ratio can go typically between 0.15 up to 0.3. So those are the typical value. The maximum and minimum theoretical values for the Poissons ratio. So usually there are some exceptions, but usually the Poissons ratio is always positive, so it's larger than 0. But Poissons ratio always have to be lower than 0.5. But usually glasses are never reach a value of 0.5. They are usually maximum around Poissons ratio of 0.3. So what happens when you insert some network modifier inside silica? So here you can see for sodium silicate and for potassium silicate the evolution of their Young modulus, shear modulus, and the Poissons ratio. Here the Poissons ratio has been multiplied by 100 so that we can plot it on the same plot. Otherwise the Poissons ratio, the scale of the Poissons ratio would be too low. Okay, the first thing that we can see, and that is generally true, is that both the Young's modulus and the shear modulus decreases when you add some network modifier. So this is true when you add sodium within silica, and this is also true if you add potassium. We observe the same thing, that the Young's modulus and the shear modulus are both decreasing. So this comes from the fact that the more modifier you add, the lower the connectivity of the glass, so the number of bonds decreases. The strength of the bonds also decreases. So as a reminder, you can see glass as a network of atoms that are connected by some little springs. So if you have fewer and fewer springs as you increase the fraction of sodium, so when you increase sodium, you create some non-bridging oxygen, so you decrease the connectivity. Some silicon used to be connected with each other, but are now not connected to each other anymore, so the connectivity is decreasing. You have more and more non-bridging oxygen. So you have less and less small springs within the glass. And you are also replacing some strong silicon-oxygen bonds by some weaker ionic sodium-oxygen bonds. So overall, the stiffness of the glass is going to be decreasing because you have fewer and fewer springs, and the average strength of the spring is decreasing. If you look at the Poissons ratio, it's the opposite. So in both cases, the Poissons ratio is actually increasing with increasing fraction of sodium or potassium. In this case, this comes from the fact that the more network modifier you add, the lower the connectivity of the glass. So it becomes easier when you subject the glass, for example, to a compression, to a uniaxial compression. Since it has a lower connectivity, it's easier for the atoms to reorganize. So it's easier for the atoms to expand. Okay, so the Poissons ratio, the lateral expansion will be higher for less connected glasses. So here what we see that in both cases, the more modifier you add, the lower the connectivity, so the higher the Poissons ratio. The other explanation for this is that the more modifier you add, the modifier tends to fill the voids left in between the silica network. If you start from pure silica, this is a very poorly filled network. There is a lot of empty space left in between the silicon tetrahedron. When you add the network modifiers, so sodium or potassium, they will fill the void, so the packing of the glass will typically increase. The packing density of the glass will increase. And again, when the packing density of the glass is increasing, typically the Poissons ratio will be increasing. Why? Because if you have a glass with a low packing like silica, when you put it under pressure, for example, if you put it under compression, it's very easy for the atoms to just reorganized to fill the internal space that was left within the glass. So in that case, the glass doesn't need to expand laterally. But if the glass has a high packing to begin with, if there is not so much space left in between the atoms, then the glass will have no choice but to expand laterally to be able to accommodate the stress that is applied. In that case, there is no internal porosity within the network, so the atoms have no choice but to laterally expand to be able to release the stress that is applied. And this will result in a higher Poissons ratio. So typically, the more network modifier you add, the higher the packing of the glass, and as a consequence, the higher the Poissons ratio will be. So let's now take the example of germanium selenium. So germanium and selenium is a good example to be able to understand the effect of connectivity on the stiffness properties of glasses. The reason is that in germanium selenium you can continually change the fraction of germanium and selenium, so you will have more and more bonds when you add germanium, because germanium has a coordination number of 4, and you will have fewer and fewer bonds if you add selenium, because selenium has a coordination number of 2. And the good thing about germanium selenium is that the bonds between two germanium, between two selenium, or between one germanium and one selenium have roughly the same strength, which means that the average strength of the bonds is not changing so much when you change the composition of germanium selenium. The only thing that is changing is the number of bonds. So here in this table, you see first the connectivity, so the average coordination number of the glass, which can be calculated if you have a germanium selenium glass with a fraction x of germanium and 1 minus x of selenium. You can calculate the average coordination number by saying that the average coordination number is the fraction of germanium times 4, the coordination number of germanium, plus the fraction of selenium, 1 minus x, times 2, which is the coordination number of selenium. So this tells you that the average coordination number is going to be 2 plus 2x. So the average coordination number is increasing with the fraction of germanium. So in this case, what we see is that for a different fraction of germanium, so when you have 0 germanium, 5%, 10%, etc., up to 100% pure germanium, the coordination number is increasing. You go from 2, this is where you have only pure selenium, so this is the case, pure selenium, and you go up to 4, which is when you have 100% of germanium, so in that case you have pure germanium. And in between, you have a different concentration of germanium and selenium, so you have an average coordination number that is just increasing monotonically with the fraction of germanium. So in this case, what you can see is that the higher the connectivity, so the higher is the coordination number, the higher will be first the Young's modulus. So here you can see the Young's modulus. The Young's modulus is increasing from around 2 gigapascal up to a very large value of more than 100 gigapascal for pure germanium. And in between, the Young's modulus is just gradually increasing. Same thing for the bulk modulus. The bulk modulus goes from around 9, 10, again increasing as you increase more and more the fraction of germanium, and again becomes very large for pure germanium. And the Poissons ratio, on the other hand, is decreasing. The higher the connectivity, the lower is the Poissons ratio. Okay, again, so this is the same thing. The higher is the connectivity, the more bonds you have, so the more little spring you have in between the atoms within the network. So in that case, if you have more bonds, then the overall stiffness of the glass is going to be increased. So both the Young's modulus and the bulk modulus will be increasing with increasing fraction of highly coordinated germanium, because it creates more bonds. So the stiffness of the glass is increasing. On the other hand, this is the opposite for the Poissons ratio. If the connectivity is increasing, then it becomes more and more difficult for the atoms to reorganize. So it becomes more and more difficult for the glass to expand laterally when you apply uniaxial pressure, uniaxial compression. In that case, it means that the Poissons ratio will be decreasing as you increase the connectivity. You go from a Poissons ratio of around 0.32 up to a Poissons ratio of 0.21 for pure germanium, when it becomes very difficult for the atoms to reorganize and to expand laterally. So now the last question that we would like to address is, what is the atomistic origin of stiffness? How can we understand how the force that the atoms are applying on each other contributes to make a material stiffer or softer? What is the atomic interpretation of the origin of the stiffness of an atomic network? What we know is that the energy between each pair of atoms will somehow look like this. So if you look at the energy between each pair of atoms, it always follows a trend that looks like this, in the sense that at infinite distance, so at infinite r, the atoms don't see each other. They are infinitely far from each other, so the energy should go towards zero. The atoms do not interact with each other anymore. At very small distance, it's impossible to have two atoms overlap with each other. In that case, that would cost you an infinite amount of energy. This comes from the energy that you need to have the two electronic clouds of the atoms overlap with each other. So you cannot have the two electronic clouds overlap with each other, or it costs you a lot of energy. So the energy of the interaction between the two atoms would increase to plus infinity as the distance between the two atoms becomes close to each other. And in between, you have usually a minimum of energy between the two atoms when they are at a given distance r naught from each other. And in that case, you get a corresponding cohesive energy U0. This comes from the fact that you have at this point a balance between the Coulombic energy, the repulsion energy, and the van der Waals energy, so that you have a local minimum of the energy, and that will give you the average position of the atom. So if you have an atom at r equals 0, a central atom here, then it means that you are very likely to find that its neighbor will be at a given distance r naught from this central atom. Why? Because this is a position that minimizes the energy. So now the question is, what happens if you are compressing or putting under tension this material? So if you are doing that, starting from the equilibrium position where the atoms are initially at a given distance r naught from each other, which is the equilibrium distance, if you are trying to compress or put under tension the material, what you are doing is that if you are trying to compress, you will force the atoms to come closer to each other, so the distance r will become smaller than r naught. But if you are putting the material under tension, what you are doing is to increase the distance between the atoms, so the distance will be larger than r naught. So the question is, if you are trying to force the atoms to become closer or further away from each other, it is going to cost you some energy. And if the energy increases, it means that you will have a force acting on the atoms. Okay? And this force comes from the stiffness of the material. So what is the relationship between the energy of the atoms and the corresponding stiffness of the material? So the first thing we can say is that if we start here at the r equal r naught, which is the equilibrium condition, if you slightly decrease the distance between the atoms, the energy is increasing. If you slightly increase the distance between the atoms, the energy is also going to increase. So you are at a minimum of energy, and if you increase the distance or decrease the distance, the energy will be locally increasing in both conditions. So this can be approximated by a harmonic function or a second order polynomial. You can always do that when you have a function that shows a minimum. You can always locally approximate it by a second order polynomial. Why? Because here if we do a Taylor expansion of the function around R naught. So we can always do that. We can say that UR is a function of R. You can always do a Taylor expansion of this function around R naught. Say that first this function is going to be equal to the value of the function at R equal R naught, which is U0, plus the first derivative of the function with respect to R at R equal R naught times R minus R naught. So this is the first degree expansion of the Taylor expansion, plus the second degree of the Taylor expansion, which is 1/2 of the second derivative of the energy with respect to R taken at R equal R naught times R minus R naught square, etc., plus the third degree, fourth degree, etc. So now if we look at those different terms, so U naught will have a given value. This is the cohesive energy. This is the energy of a pair of atoms when they are exactly at equilibrium, exactly at R equal R naught. They have a given cohesive energy. This is the energy that you need to provide to the two atoms to separate them from each other. Then if we look at the second term, this second term is the first derivative of the energy with respect to R at R equals 0. But since R equal R naught is the minimum, the position for which you get a minimum in the energy, then the first derivative is going to be equal to 0 at this minimum. You have a minimum, so the derivative is 0. So this term is going to be equal to 0. That's why in that case you need to go to the second term of the Taylor expansion. And this term is not 0. In this case, there is no reason for this term to be 0. This term is the second derivative of the energy with respect to R. So this term captures the curvature of the energy. The curvature of the energy potential at R equal R naught. So this is the curvature of the energy potential, the energy of interaction between the atoms at the equilibrium. So the higher is the value of the second derivative, the higher is the curvature. For example, if you had a very high curvature, a very high second derivative, you would have a more peaked minimum like this. If you have a lower second derivative, then you have a function that is less curved with a more shallow minimum like this. So this term here tells you about the curvature of the energy potential. And this is a very important term because this is what will dictate the stiffness of the material. So what we can do is that we can realize that this looks like very similar to the energy of a spring. If you have 2 points that are separated away from each other and attached with a given spring with a spring constant K, then the energy is given by 1/2 times the spring constant K times the elongation to the square, the elongation being the distance L between the 2 points minus the equilibrium distance L naught when the spring is at equilibrium with no force being applied to the spring. So this expression here that we get for the energy between the two atoms looks very similar to the energy that you get for a quartz, for a spring. So what we can do is to just say that we can rewrite this energy U of R as the term of the energy at minimum, so U naught, plus we can say that we can rewrite the second derivative of the energy as being equal to K. We can define K being the second derivative of the energy with respect to R at R equals 0. And if we also define delta R being the elongation is the difference, the distance between the two atoms minus the equilibrium distance. So the same thing as for a spring. How much, if you elongate the bond, then delta R equals 0. You have an elongation of the bond, and delta R will be negative if you have a shrinkage of the bond, if you force the two atoms to become closer from each other. In that case, so you can say that the energy between the two atoms as a function of their distance is equal to U naught, the energy of interaction, the minimum of the function, plus 1/2 of K delta R square. And in that case, those two expressions, so the expression of the energy of the atoms as a function of the elongation between the two atoms, becomes very similar to the energy of a spring. Then the next question is, how does it relate to the stiffness of the material? How does it relate, for example, to the Young's modulus of the material? So what we can say is that if we take, for example, let's take just a crystal model to make it more simple. So you have all the atoms of the network, and the distance between the atoms at equilibrium is going to be R naught. R naught is the distance between each pair of atoms. So this is the distance between the atoms within the crystal. So what you can say that each atom can be attributed, the space available to each atom is a small cube. Each atom belongs to a small cube, and each cube has a volume R naught to the power 3. Okay, each cube has a length R naught. So if you look at the volume associated to each atom individually, the volume of each atom is R naught to the power 3. So how can we get now an estimation of the Young's modulus of this material? So the question is, what is the force that you will be applying on those atoms as a function of their elongation? So what we can do is first calculate the force, because the force is the derivative of the energy. So we know that the force is minus the gradient of the energy. So we have the energy already as a function of the elongation. So we can say that the force as a function of the distance between the two atoms is the derivative of first derivative of U naught. This is a constant, so this derivative is 0. And then we have to take the derivative of this function. So the derivative of this function is just minus k times delta r. Okay, you derivate delta r2, that gives you 2 delta r, so the factor 1/2 disappear, and the force now becomes minus k delta r, which is the same as the force created by a spring. If you try to deform a spring with a deformation delta r, then the force is also given by minus k delta r. So this shows you that the bonds between the atoms can really locally be approximated by a spring with the same energy and the same force as the one that you get for a spring. So now the question is, how is this related to the Young's modulus? So what we can say is that we can say if we take two atoms and try to calculate what is the force that you have to apply to deform those two atoms. So if you have those two atoms being attached with a little bond, and let's assume you apply a force to this bond, and you want to look at what is the relationship between the stress and the strain for this material. So here, since each atom belongs to a small cube of a dimension R naught, so the dimension of this bond here will be a small rectangle, where here the surface that belongs to each atom is given by R naught, and then you will find another atom if you look at a larger distance. So the question here, if you apply a stress sigma on this bond, what kind of strain will you get? So we can first calculate the stress. So we can say that the stress in this case is given by the force that you apply divided by the area. In that case, the force, if we take the absolute value of the force is given by k delta r. This is the force that you need to elongate the spring. And what is the area? The area is the area of the surface over which the force is applied, which in this case is R naught to the power 2. And what is the corresponding strain? So to get the strain, we need to look at the relative elongation. the relative elongation is the absolute elongation delta r divided by the initial distance, and the initial distance is r naught. So the strain is given by delta r divided by r naught. Then what we can do finally is to use the Hooke's law. The Hooke's law tells you that the stress is proportional to the strain and that the proportionality constant is the Young's modulus. So this is what the Hooke's law tells you. So here we have an expression for the stress and for the strain. So we can replace stress and strain in this expression. So what you get is that the constant K times delta R divided by R naught square is equal to the Young's modulus E times the strain, which is delta R divided by R naught. So what do you get at the end? You get an expression for the Young's modulus. The fact that the Young's modulus will be equal to K, the delta R term disappear. You have also R naught that can disappear. So you find that the Young's modulus is K divided by R naught. Then if you want, you can also have a different type of expression. The question is, what is R naught? R naught is the distance between each pair of atoms. So we can also re-express it in terms of the local density. What is the density? This is the number of atoms per unit of volume in your material. Here, if the volume for each atom is R0 to the power 3, then it means that the number of atoms per unit of volume can be given by 1 divided by R0 to the power 3. This is because you have one atom for a volume of R naught to the power 3. So the density is given by 1 over R naught to the power 3, which means that you can also do the opposite and say that the distance between two atoms at equilibrium is equal to 1 over the third square root of the density. So if you combine those two expressions, what you can find is that the Young's modulus is given by K, which is the curvature of the energy potential, times the third square root of the atomic density. Okay, so this gives you an atomic interpretation of what is the Young's modulus of a given material. So you have K. K is the second derivative of the energy between each pair of atoms calculated at the minimum. This is the curvature of the potential, of the energy potential between each pair of atoms. And then you have the second term, which is rho. Rho is the atomic density. So the atomic density, the number of atoms per unit of volume. So these terms capture how many atoms per unit of volumes do you have. And all those two terms are important to capturing the Young's modulus. Why? So the first term first tells you that the curvature, the higher is the curvature of the energy potential, the higher is the Young's modulus. So this is the first important result. If you look at the energy between each pair of atoms, the curvature of the interatomic potential tells you about the stiffness of the material. It means that if you have a first material that have some bonds like this with a low curvature, or if you have some material that have bonds with a higher curvature like this, the curvature here of the potential, so this curvature, this is a low curvature, or on the other hand, this would be a more peaked potential. This is a higher curvature. And if you continue like this, you can also draw a very, very high curvature like this, which would be an even higher curvature. So the curvature tells you about the stiffness. K, the second derivative, the higher is K, the higher is going to be the Young's modulus. So typically you see here that since if you have atoms that have the same distance R naught with each other, it means that the minimum of the position is not going to change. You also know that the shape of the function is not going to change. The shape of the energy as a function of distance is always the same. You know that whatever you do, the energy should go to plus infinity at when the distance becomes very small. You know that the energy should go to 0 when the distance becomes infinite. So this shows you that the curvature is very linked to the value of the energy at the minimum of the position, the position at which you have a minimum of energy. If you have a low U naught, that is to say, if the value of the energy at the minimum, at the distance for which the energy is minimum, if this corresponds to the low value of energy, then it means that you will have a low curvature. If you have a higher energy, if the energy at the minimum is higher, if you have a higher cohesion energy, then it means that you will have a more curved potential energy. It means that the curvature, the factor K, will be higher. The second derivative of the energy will be higher, which means that the higher the cohesive energy, the higher the curvature, so the higher will be the Young's modulus. So this tells you why when you have some bonds that have a very high energy, for example, silicon, oxygen, those are network former. The energy between those two bonds is going to be very high. They have a strong energy. In that case, the energy between those two atoms is going to be very peaked. You will have a very high cohesive energy U0. In that case, you will get a high curvature. So you will get a high Young's modulus as well. If you look, for example, at network modifier, for example, sodium, oxygen, then the energy between sodium and oxygen is much lower. The energy between network modifier and oxygen is much lower. In that case, it means that the U naught, the cohesive energy, will be lower. In that case, it means that the curvature, here the curvature will also be significantly lower. So you will have a lower curvature, so you will also get a lower Young's modulus. So that's the first thing. This is the interpretation of why the higher is the cohesion energy between the atoms, the higher will be the Young's modulus. So that's the first thing. The second thing here is about the number of atoms that you have. Here, this term tells you the density. It tells you that the more atoms you have per unit of volume, the higher will be the Young's modulus. This comes from the fact that the more atoms you have within your system, the more bonds they will create per unit of volume. So the more little springs per unit of volume you will have in your glass. So if you have more bonds, more little spring, then this is also going to increase the Young's modulus. So you see here that the Young's modulus has two main contributions. First, what is the stiffness of each individual bond? So the stiffness will be higher for the bonds that are created by the network formers and will be lower for the bonds created by the network modifiers. So this tells you that the higher the bond energy, the higher will be the Young's modulus. The more network former you have with respect to the network modifier, the higher will be the Young's modulus. So the higher the connectivity of the glass, the less non-bridging oxygen you have, the higher will be the Young's modulus. So this captures the effect of the connectivity and the strength of the bonds. And then you have this second effect, which is the effect of how many atoms do you have per unit of volume. And here you can see that the more atoms you have per unit of volume, then the more little spring you will have within the atomic networks, so that the higher will be the Young's modulus. Okay, so that's all you need to know for the stiffness of glasses. Again, the main conclusion is that the stiffness depends at the same time on the connectivity of the atoms and the packing of the atoms. How many atoms do you have per unit of volume? How many internal porosity do you have in between the atoms? Those are the two main ingredients that will control the stiffness of glasses. So to be able to understand how changing the composition of glasses will also change their stiffness, to be able to develop new glasses with either very low stiffness or very high stiffness, what you need to know is some information about the structure of the glass. What is the connectivity of glasses as a function of their composition? What is the packing of the atom as a function of their composition? If you are able to predict for a given glass, a given series of glass, how the connectivity, the number of non-bridging oxygen, etc., is changing as a function of their composition, then you are able to predict how the stiffness of those glass is going to change as you change the composition. And you can use this knowledge to predict what will be the ideal composition that will either minimize or maximize connectivity based on the kind of stiffness that you want for your glass. Thank you for watching, and the next chapter we will be talking about the hardness of glasses.